Planets in binary stars by Professor Heike PILAT-LOHINGER.
Yes.
Please.
So thank you, and thank you to the organizers for giving me the chance to present my work, or our work, in fact, because this work has been done in collaboration with several collaborators from Vienna, David Bancelin, Bazso, Siegfried Eckel, Barbara Funk, and Markus Görkowitz. And we study the habitability or the conditions of habitability. Doesn't it work? Is it better now? Is it better?
The same.
It's the same.
Push the button.
No, it doesn't work.
Okay.
Is it better? Yes. Okay. So, together with my colleagues, we study the conditions for habitability of planets in binary stars, and this is in the framework of a national project called Pathways to Habitability. And what's the motivation for doing such studies? First of all, so far a lot of planets have been detected, and of course we are now looking, or the observers are now. Okay, it doesn't work. No. Can you hear me in the back if I talk loud enough? Okay, so thank you. Okay. And of course, observers are now looking for an exo-Earth. And as we know that in the solar neighborhood, lots of stars form binary and multiple star systems, it's interesting what are the conditions for planets moving in such stellar systems. And of course, the question is, if we detect a terrestrial-like planet in such a stellar system, could it be habitable or not? And what's the difference to our solar system? So for that, we have on the webpage of our group, of the ADG group, a binary catalog installed. This is maintained by a colleague in Vienna, by Richard Schwarz, and where you can find an already huge number of exoplanetary systems hosting that are hosted by binary stars, and also several systems in multiple star systems. And if we consider binary star systems, we have to take into account different types of planetary motion. So in fact, the planet can move about one star only, which is called circumstellar or S-type motion, or the planet can move about both the stars, which is usually called circumbinary or P-type motion. And it's obvious that a perturbing star causes stability limits for planetary motion. So in fact, stable planetary motion is restricted to certain region, where for the S-type or circumstellar motion, we have an outer critical stability limit, and for the P-type or circumbinary motion, we have an innermost critical orbit, so there must be a certain distance from the two stars that the planetary motion is stable. Okay, so we know from the solar system that you will not find habitable planets everywhere. There is a defined zone around a star, which is called habitable zone, where liquid water can exist on the surface of a terrestrial-like planet. And of course, this zone depends on the stellar, on the parameter of the stars, on the stellar type, on the mass, on the age. Also on the parameter of the planet moving in this zone, on the mass, on the composition, on the atmosphere, and of course on the whole architecture of this system. So here you see a schematic view of the habitable zone for the solar system, where we see that in fact it's not a large region, and it depends on different definitions. For instance, an old definition, a very conservative definition by casting, gives a very restricted, a very small region around the Earth for the habitable zone, which is the region between 0.95 and 1.4 astronomical unit. Later studies by Forger and Couperapou, for instance, showed that the outer border can be shifted to values of 1.6 or 1.7 astronomical unit. In that case, Mars would also be in the habitable zone. But of course, the mass of Mars is too small, and the conditions of its atmosphere are not such that it will be a habitable planet. So, what we can see as well is that for low mass stars, the habitable zone is much closer to the star than for bright massive stars. Then the habitable zone is farther away. And here are the values for some main sequence stars from M to F, the inner border of the habitable zones and the outer border of the habitable zones. For the different stellar types, these values are calculated with the formula of Couperapou from 2014. And of course, this habitable zone has to be in the stable area of a binary star. That's the planet, as a necessary condition that the planet could be habitable in a binary system. Okay, with the knowledge of the borders of the habitable zones, and we know that the stability is restricted in binary systems, we calculated here, for instance, for S-type motion or circumstellar motion, for different host stars from M to F, and different eccentricities of the binary. The minimum distance on the y-axis for the different signs shows different stellar types of the secondary star. For binary configurations, that the condition is given that the habitable zone is in the stable area. So we see, in fact, for tight binaries, we have several tight binaries with, this is 10, this is 20, with where planets have been found. But in fact, if we have tight binaries, only M and K type stars with high eccentricities provide conditions, provide necessary condition that the habitable zone is in the stable area. For G-type stars, only eccentricities, well, up to 0.6, it's possible that the habitable zone is in the stable area. So first of all, the habitability of a planet depends on the parameters of the binary system, especially on the stellar types and on the eccentricity of the binary system. Okay, what we know from our different studies is also that the secondary, if you start, that the secondary causes eccentric motion of the planet. In fact, if you start, if you consider the motion of a single planet around an isolated star, you have the two-body problem, and if you start this planet on a circular motion, it will remain circular for all the time. If you do the same in a binary system, then the planet gets an eccentricity depending on the eccentricity of the binary. So the higher the binary's eccentricity, the higher will be the variation in eccentricity for a single planet in moving around one stellar component. And what we've seen when calculating the isolation, the insolation of on this planet, we see the same variation in the insolation like for the eccentricity. So in fact, a planet gets more insolation due to the, or has a variation in insolation due to the eccentricity motion of this planet. Due to this effect, Siegfried Eckler defined different habitable zones for planetary motion in binaries, where he defined a permanently habitable zone where the planet is always in the habitable zone, an extended habitable zone where the planet could leave the habitable zone only for a short while, and the average habitable zone where higher eccentricities are possible, and in fact the planetary orbit could be mostly outside the habitable zone, but in average the conditions are such that the planet could be habitable. Okay, so what we've seen is, in fact, as we know that a planet will get an eccentricity when moving in a binary star system, we found that at each pericenter passage of the binary, there's a sudden increase of the planetary eccentricity, so that we studied this perturbation on a giant planet moving around one stellar component in a binary system, and looked at the perturbation on the habitable zone. And in fact, this could cause, depending on the architecture of the systems, to a secular resonance in the habitable zone. And from this, we ask ourselves if eccentric planetary motion in the habitable zone is habitable or not. First of all, we have secular perturbation in the habitable zone, and we have also stronger perturbations in the planetesimal disk. This is important because habitable, as we do not know if planets form dry or wet. We have to study also for the habitability of planets the water transport to a planet in the habitable zone. So with more perturbations in the planetesimal disk, we are lucky because we can transport more water to a planet in the habitable zone. What we have seen by comparing the water transport in a binary star system, these are these two histograms, compared to a simple system where a single Jupiter orbits a sun-like star, where we took, in fact, the same disk around the isolated star and the circumstellar disk in a binary, and we see, in fact, the perturbation, the additional perturbation of the secondary causes a stronger perturbation in the planetesimal disk and can transport more water to a planet in the habitable zone. In fact, we also divided the habitable zone into an inner part, two central parts and an outer part. And what we've seen that, in fact, in the binary, the water transport is into the whole habitable zone, while in a similar system where we ignore the secondary, only the water transport is only in the outer part. So, in fact, this would mean, this is for a G-type star, that if there is only one Jupiter at Earth's position, there would be no water transport to Earth's position in that case. Only, well, in Mars position, around Mars position, the water is transported to the outer part of the region. This is also for this is the result for a tight binary with a distance of the secondary of 50 AU, and this is the same study for a distance of the two stars of 100 AU. We see, in fact, in that case, the difference is not that strong, but due to the perturbation of the giant planet from the secondary, we see, in fact, that the water is transported to the whole habitable zone, while in the isolated star only, again, to the outer part. So for the eccentric motion of the planet in the habitable zone, we in fact calculated the water transported to a planet moving on an eccentric orbit in the habitable zone, and to nearly circular motion in the habitable zone. And if we count the water by the usually the hit and stick mechanism, we see that the water, it's such a planet on an eccentric orbit could collect more water than a circular on a circular orbit. But if we study for such a planet also the impact velocities and the impact angles, we see that the impact at resonances, the impact angles are much higher than for circular planetary motion. And when we do SPH simulation and study the water loss during impacts, we see that the higher, of course, the higher the impact velocity, more water is lost. And in fact, if we look now at the red and black full lines and on the blue line, then we see that this is, one slide and I'm done. That the eccentric motion would not cause a higher water transport than circular motion. And in fact, okay, I skipped this. In fact, what we think is that it's quite questionable that in tight binaries we might find habitable planets. There is a better chance in white binary star systems for S-type motion, and for P-type motion, that's what I've not shown, is that we have the problem of colliding winds, where the planet in the habitable, so these colliding winds cause shock fronts, and of course the planet moving in the habitable zone has to pass these shock fronts, and there are ongoing studies that have to clarify if such a planet and passing several times such a shock front can be habitable or not. So thank you.
So unfortunately we are 2 minutes beyond the 20 minutes. So maybe if you have questions you can ask later during the break. That's okay? Thank you very much again for